So I've been given the distressing task of talking to you about fat tails in climate change and climate economics, in particular focusing on climate sensitivity. So I'll say something about these things, and so the focus of the workshop is climate sensitivity. A lot of the talk will be about that, and some of the things you'll have seen before. This is the cost of going after lunch and talking about science when you're not a scientist. You can hear me? No? Better? Yes, okay. But I also, I'll also talk a little bit about sort of some reflections on the process of economic modeling and what we should maybe be doing with our economic models to make them useful for policy making. This is really what I'm interested in, is making good decisions in the real world. And I think models are an indispensable part of that task, but they are contentious. So I sort of start provocatively with a couple of quotes. One, advocating the benefits of abstraction by a non-economist, and the other, excoriating economists for purely being abstract by an economist. Okay, who's not a modeler, which is, I mean, that may or may not be a sort of a thing in his favor. I don't know. So Primo Levi says, you know, we're compelled to reduce the noble to a schema. That's really what modeling is, right? We can't make decisions in the world if we say, well, everything's just so bloody complex we can't see, you know, our way through the cloud. And Boulding was sort of fundamentally skeptical of the role of mathematics and abstraction in economics. Sort of, you know, mathematics brought rigor to economics, but unfortunately also brought mortis. And I think that, I mean, that's certainly going too far. But there is something in this idea that once you've finished modeling something, you're done, right? So I think that may well be true from the perspective of seeing modeling as a purely intellectual exercise. But when you take a model into the real world and people's livelihoods are suddenly on the line based on the decisions that you inform with that model, there's a new kind of set of issues that become relevant to assessing what we mean by model quality and the usefulness of the model. So I'm going to make 5 very simple points. One point, some of them have been made before, so I'll do them sort of quite quickly. One is that we don't know the right distributions of climate sensitivity, and I'll argue that that's okay. You know, don't worry about it. The other is we're unlikely to learn about the distribution of climate sensitivity, or at least we're unlikely to learn about it much faster than we observe things. Right? The third is that fat tails and catastrophes pose problems for integrated assessment models, but they're not a priori insurmountable. The fourth point is that climate sensitivity is probably not the most important uncertainty in integrated assessment models. And we must beware of the streetlight effect. And I'll explain what that is in a minute. And the fifth point is that we should do everything we can to quantify the structural uncertainties in integrated assessment models empirically. So basically what I'm interested in is how wrong could we go by using these models and the structural relationships that are in these models. Okay? So what does an integrated assessment model look like? Well, it looks something like this. So usually what you do is you have a bunch of scientific inputs. You have some a climate model forced by emissions from economic output, and those emissions drive temperature changes, which drive impacts on the economy, which we value in some way. There are assumptions about how technologies change, how the decisions that we make about savings and mitigation translate into economic productivity and into emissions. And there are assumptions about how those emissions and changes in temperature translate into economic damages. Then we sort of take this soup, give it a good stir, and we evaluate it using very, very well-established methods in economics. And something called an evaluation framework, which is basically a way of aggregating benefits and costs that are distributed over states of the world and time and people, if you have a regional model. And we make our policy recommendations. I'm going to argue that, you know, each of these links in the chain is uncertain, but the uncertainties are not the same. There are uncertainties that come from different components, and we need to understand and probe those uncertainties as much as we can in order to make the models relevant for policy. So this you've seen before. So climate sensitivity, in fact, this is, I think, the third time you're seeing this today. So, climate sensitivity distributions, what does the science tell us? Well, here's a bunch of models that are taken from the scientific literature collated by Meinshausen. What do economic models usually assume? They usually assume it's something like that. So what I've done there is just taken an equally weighted average of all of those distributions. And in fact, a lot of the models would just assume that there's a delta function, right? That there's a single known value of climate sensitivity and then do sensitivity analysis over that value. So the point, so Jeff's talked a lot already about the sort of difficulties of going from here to here. And Bill's already talked about the desirability of going from here to here. And I have sympathy with both points of view, right? I would love to be in a world like this. But I also recognize that we're probably in a world like this, and we're unlikely to go from here to here without introducing quite a lot of subjectivity into the analysis that we're doing, right? Now, maybe you're comfortable with that. But I think that subjectivity is something that policymakers need to know about. They need to know that you're putting some assumptions onto the data or onto the models that are, in some sense, independent of their empirical structure, right? So whether you do that by running an integrated assessment model with each of these distributions and outputting 20 values for the social cost of carbon, or you sort of aggregate them in some way and you make those subjective weighted judgments, but have a modeling framework that allows you to maintain a distinction between subjective and objective, it's a sort of methodological choice. And I think both of them have applicability. So learning about climate sensitivity. So I think Gary talked about the value of information. I think he wasn't really talking about climate sensitivity. He was talking about a sort of adaptation decision. But I think there's been quite a lot of work. In fact, I think Bill's done some of the work on the value of information about climate sensitivity, and certainly Charlie Kolstadt and David Kelly in Miami have worked on this. And this idea that, well, the value of information about climate sensitivity is clearly very high. We would be much better off if we knew its value than having to make this decision under sort of a lot of risk. Unfortunately, history suggests that that value is not realizable. Right? It suggests that the only way that we're going to learn about climate sensitivity is by observing stuff, and those observations are going to become realized in real time. Right? We're not going to have some technological or scientific silver bullet that really narrows this distribution of climate sensitivity. And I'll argue that even if we did, there would still be a role to play for the tails of this distribution. So here you're looking at the estimates over time. So here's one going back to the 1880s. And this is, by the way, stolen from Steve Schwartz's website. The distributions, certainly in the last 20 or 30 years, really haven't changed all that much. We've maybe become more confident about those distributions. And maybe we understand where they come from and how the data constrain the distributions more. But in terms of looking at the range of possible values, it hasn't changed a whole lot. So that seems to have quite a lot of consequences for how you would want to make policy, right? So you can assume that, in fact, there are arguments in economics that suggest, well, irreversibility and learning are coupled things that have a strong effect on the policy choices you want to make. So if you can afford to delay an irreversible decision, like installing some renewable energy capital, for example, and wait for more information to learn about the benefits of that installation, you should. But that is conditional on that information becoming available on policy-relevant timescales. And arguably, we have sort of 40, 50 years to really kill this climate problem or to make serious inroads into it. And arguably, on those timescales, climate sensitivity is not going to change very, very much. So I would argue that really the policy decisions we're going to make are basically going to have to be based on the kind of information that we have at the moment.
When you say sensitivity is not going to change, or knowledge of it's not going to change?
The knowledge of it. Yeah, sorry. Good clarification. You've seen, Steve showed you a picture a little bit like this before. So here, the crucial thing with climate sensitivity is that climate sensitivity is inversely related to the things that you observe, right? So when you have uncertainty in the things that you observe, that translates into a skewed distribution for the thing you care about. And it's skewed and moreover fat-tailed. And so this sort of, the top of this distribution of uncertainty and feedbacks really drives the uncertainty in climate sensitivity. So here, if you look at the difference between the solid and the dashed lines, what's happened, we've narrowed our uncertainty in in the feedbacks. And if you look at the tail, it's sort of indistinguishable, right? So there's a shift in the mode of the distribution, but the tail really doesn't change very much at all. And that's really because, well, there are a couple of reasons. One is this inverse relationship. The other is that, well, we're observing stuff today that is that's reflective of the climate today, right? So to expect to get a bunch of information about very, very high temperature world from observations that are sort of based in today's climate is a bit too much to ask. So this tail in climate sensitivity, some of it is driven by the fact that you're making this linear approximation for very high values of feedback, and those are physical values up there. So a climate sensitivity of infinity, which, by the way, these distributions have put weight on, it's unphysical. I mean, obviously, the value of climate sensitivity is bounded by the temperature of the sun, or the temperature of Venus, or something like that. But it doesn't matter. And the point is that you don't care about climate sensitivity per se. What you care about is damages. What you care about is economics and livelihoods. And this is something you really care about, even up at 10 degrees here. I mean, we would be in serious, serious trouble if we find that climate sensitivity is in that tail. So one point that I think hasn't been made just yet is that although high climate sensitivity values are very concerning, the temperature trajectory realizations on those values are delayed, and they're delayed quadratically in the value of the climate sensitivity. So the higher is climate sensitivity, the longer it takes you for the temperature to reach that high value, and the sort of quadratic dominates the linear, right? Which means that at any given point, the distribution of temperature is actually probably bounded, right? So this is something that's illustrated in a nice model by Baker and Rowe. It's a nice little analytical model of the climate system. And you can see that as the time scale gets really, really long, the time it takes to reach these high values goes up. I mean, the important point there is that we're actually going to a logarithmic scale here in time. So for very, very high values of climate sensitivity, this is a probability distribution of the climate sensitivity. So for high values, it's taking a really long time to get there. That's really important knowledge for economic models because we discount stuff that's far off, right? So if these, and the other reason, of course, is that it just gives us a lot more time to react, a lot more time to develop technologies to suck CO2 out of the atmosphere, for example, or solar radiation management, or whatever the case is. So the fact that these very, very high temperature trajectories are probably deferred, even if climate sensitivity is high, is important for policy making. So Marty has pointed out that largely motivated by looking at the distribution of climate sensitivity, although I think it's a mistake to see his argument purely in terms of climate sensitivity. What he's really talking about is damages and changes in consumption growth rates. Marty's talked about the fact that fat tail distributions sort of really illustrate a form of non-robustness in these integrated assessment models, in the sense that you can make very small changes to the assumptions the models make about the distribution of consumption growth or temperature change, and get them to sort of spit out the fact that, well, what you should be doing is paying your entire income today to avoid these fat-tailed risks tomorrow, right? Now, a simple way of seeing this argument is that, well, to see that welfare in these models it's in some integral over uncertain stuff, right? And in the standard parameterization of these models, you can basically boil this down to some integral over temperature. Temperature to some power, some negative power. And by writing down the assumptions in the models about how consumption relates to damages and how utility relates to consumption, you can actually solve for what this parameter is, what this sort of scaling law at the high temperature is for welfare. And it looks something like this. It's basically a component that comes from the temperature distribution. Right? So that's the exponent of the temperature distributed at high values, how quickly the distribution is decaying to zero. There's a component that comes from the damages, which tells you how quickly damages are escalating as temperatures go very, very high. And there's a component that comes from the utility function you assume in the representation, which tells you how much you value those damages, right? How much do you care about the fact that your consumption is going very, very low? So I think this is actually quite a neat representation of the things that we care about in an economic model. modeling. One is the science, the other is the economic impacts, and the third is the preferences, right? So, yeah. Sorry, this is for the scientists in the audience. Yeah, it's constant coefficient of relative distribution. Yeah. So the point is that if this guy is less than 1, the welfare is minus infinity, right? So this is something that you should really care about in the economic models. And it turns out that it's actually rather easy to find values of the parameters where this is less than 1. So in the standard models, the temperature exponent distribution is probably 2. Certainly the Rowe-Baker distribution has an exponent of 2. In Bill's model of damages, the damages decay or increase like a quadratic function of temperature at high damages. And utility curvature, let's treat that as a parameter. You can solve for the value of utility curvature that makes delta less than 1 with those parameter values, and it turns out to be about 1.5. And usually the values of the parameters that we use in these models are about 2. So you certainly can't rule out this dismal theorem based on the standard models. And I think that Marty should really be sort of applauded for pointing out this importance of these kinds of uncertainties and catastrophes in these models, and the fact that they may be non-robust to sort of small changes in the distributions that we assume for the parameters. However, my reading of this result is not that it's a sort of paralysis of economic modeling. It's pointing out a non-robustness, so you have to seek the origins of non-robustness, and then ask whether the criteria that are necessary for that non-robustness to occur are sort of irredeemable. I mean, what can we do to remove that non-robustness? And it turns out that, well, basically when it comes down to it, it sort of relies on the choice of utility function, which we've used for decades because it's what growth theorists use, and it gives you balanced growth paths in analytic models. But for the purposes of this kind of numerical modeling, there's absolutely no reason to choose that utility function at all. Moreover, once you bound the utility function below, policy choices are insensitive to the high tail, right? So that's just a simple continuity result. If I imagine there is for any loss of a given size, there must be some probability of that loss small enough that I sort of don't care about it, right? So if I can reduce the probability of that loss as small and small and small, I eventually just don't care about that loss at all. And policy choices should reflect that kind of continuity argument. So the point, great, thanks. So the point is that there are actually lots of ways to sort of get rid of this non-robustness in the modeling, but each of them requires us to change the welfare framework that we're using in these models. And that's one of the take-home messages I want to send is that, well, welfare frameworks are just as important as empirical inputs for the policy recommendations of these models, right? So the choices that we make about welfare frameworks should really be explicit. So I think that's the sort of take-home message of the dismal theorem. At least my take-home message is that we need to probe the effects of these assumptions that we're making in the models and see how they affect the policy recommendations from the models and present that to policymakers, present a sensitivity over it. So I've talked a lot about sensitivity and temperature, but is climate sensitivity a dominant uncertainty? And are we not just looking for our keys under the lampshade, right? Under the street lamp? Because climate sensitivity is really one of the best quantified uncertainties in economic policy and analysis of climate policy. It's because it's a scientific quantity. It's not an economic quantity. It's something that we can go out and measure, as Steve illustrated. And it's really very well quantified, despite the fact that we have lots of different distributions over it. And you can ask, well, just look at the integrated assessment models. Which parameters in these models dominate the policy outcomes, the policy recommendations? And here's a result from a recent study by Saltelli, an interesting computational study by Saltelli, who's done a global sensitivity analysis of Bill's dice model. So instead of picking a subset of the parameters of the model and holding everything else constant and then varying one at a time, what they've done is pick one parameter of the model and find the conditional distribution of some endogenous policy variable, holding that parameter constant and varying every other parameter in the model, right? And then vary the fixed value of that fixed parameter and see how much information you have of the total distribution, the unconditional distribution, by conditioning on that parameter. So how much information do you lose by just fixing that parameter on average, right? So it's a very, very global measure of the sensitivity of these models. And what they find is that really it's the damage function exponent that dominates, right? So climate sensitivity is certainly important, but it's ranked fifth, right? There are technological parameters in there that really matter, certainly those two, and there are also welfare parameters that really, really matter. And this is for the optimal carbon tax in 2015. So this is a policy-relevant parameter, right? So my feeling is that, well, you know, we economists sort of lag behind the scientists in terms of quantifying the quality of our models, quantifying what the models can and can't do and what the risks are of using them. So and there's a good reason for that. It's because we're sort of engaged in this huge out-of-sample exercise, right? We're engaged in an extrapolation exercise where we don't really have law-like behavior that determines how the economy is going to grow and evolve and behave in response to climate change. But one simple thing you can do is just try and estimate the kinds of structural uncertainties you would have in using the kinds of laws that these integrated assessment models encode by going back to the 19th century and saying, imagine that you used those kinds of structural assumptions to predict the 20th century. How well would we do on average? And here, this is exactly what I've done in this graph in ongoing work. So here, the only thing that this represents is uncertainty in something called the total factor productivity, right? So I'm assuming I know everything else. I'm prescient about for those economists in the model, about the stocks of capital and labor over the 20th century. And the only thing I don't know is the total factor productivity associated with the production function. And I can ask, well, how well would I have done if I went back to the 19th century, took 19th century data, and made predictions of 20th century economic growth using these kinds of models? And this is an example. So the black line is actual realized economic growth. And the gray lines are projections from basically training the model on different window lengths of data with different starting points. Okay, so that's how we get the distribution over growth projections here. What you can see is that actually the models do pretty well for the first 50 years. And then in the last 50 years, there's a pretty serious bias, right? So the realized value is sort of out in the tails of the distribution of predicted values. And that's really not at all surprising. So imagine what you're trying to do. You're trying to predict all the kind of technological advances that we realized in post-war 20th century, the massive increases in productivity associated with the enormous technological advances we've had. And you're doing that in the 19th century when Carl Benz had just invented the motor car, right? You cannot expect that data to be predictive of outcomes that are policy relevant in the following century. And let's be clear, the last 50 years of this century are what's policy relevant for climate change, right? And growth rates are what's policy relevant for climate change because they drive the discount rate in these models very, very strongly. So accounting for these kinds of, taking the models to data and asking, well, what are the risks associated with the structural relationships in these models seems like a kind of a weak but nonetheless necessary exercise in trying to understand what are the sort of structural uncertainties associated and the risks associated with using the model for policy. It's not to say that the models are not relevant for policy. They are certainly relevant for policy, but we need to understand the modeling risk and the decision risk from using them as well. So my feeling is that the climate scientists are actually a step ahead on this task. So here's an example where they've taken a whole bunch of, I think there were 25 models in this sample, and plotted some measure of model similarity. So how similar the models are in terms of their replication of the 20th century data against their ability to predict. So on the y-axis, sorry, on the z-axis, the vertical axis here, is their ability to, it's basically the root mean square error in their predictions about 20th century temperature or historical temperature. And it seems like it's that axis, it's that vertical axis that we're missing in climate in the economic side. We don't understand what the quality of the models is. We also don't understand how they depend on one another. And there's a good reason for that. They are extrapolations. They are best guesses for the future. But it's also, I mean, it's desirable to try and get at something like this vertical axis. So what do we mean by model quality? What do we mean by a model that's structurally sound with respect to out-of-sample projections of the 21st and 22nd centuries, which is where they're being used to inform policy, right? So my question is, can we come up with a figure like this for integrated assessment models? And if so, what would be the axes? How would we measure this thing? And that's something I really pose to the group. So what's my conclusion? What can scientists do to inform economics, and what can economists do to inform policy? Well, I think scientists, this has already been discussed this morning. I mean, we need to identify what the most relevant policy variables are, climate variables are for informing policy, and the variables that have the highest potential for uncertainty reduction, right? And so it's a sort of product of those two things that really matter. And those are the things where research effort should go into. The second thing is really sort of crossing this cultural divide and making data and models and results really accessible. And I guess that's one of the great beauties of meetings like this, is that it encourages that kind of cross-pollination. And keep telling us what you do and don't know. And the other thing is, go and read the economics literature. It's fascinating, and it's important. It's really important for taking the work that you do and making it relevant to the policy world, because that's ultimately how we transmit your information into government, right? For economists, I think we need to do much, much, much more thorough sensitivity analysis of our models and try to estimate the sort of risk of the model risk, by calibrating the structural relationships against historical data, just to get an idea of how wrong we might be by using them. Avoid incredible certitude. This is Charles Mansky's phrase. This idea that once you put a model out there and it's sort of, well, the social cost of carbon is $33.56 per ton, and that's the answer. There are no central estimates in economic modeling. There are just estimates. Right? We don't have centralized moments over these distributions. I think explore a much wider range of structural assumptions, and when we do econometric work on impacts, we need to use the full suite of climate models to force those impacts, and it's very, very strongly illustrated by work by Ted Miguel and Marshall Burke. And similarly, read the scientific literature. It's fascinating, and it's important for understanding how your models relate to the underlying science that drives them. Yeah. Thanks very much.